Give me a moment. Folks, if you haven't subscribed to our YouTube channel, I would request that you do. We keep posting a lot of material these days, putting in a lot of effort to do in a regular basis. And we are live. I'd like to introduce you folks to Chanda. Chanda and I, we were together during our PhD years. While we were working on theoretical physics, theoretical particle physics, he is from IIT Chennai, one of the rank holders. He did an outstanding PhD on black holes and quantum field theory. After that, he went back to India. He joined Infosys for a few years, and then he joined Evolve, and he joined me, and we have worked together through a startup and now in the day job that we work with. Chanda is going to talk on word embeddings. It's a topic that is central to natural language processing. In any language, there are lots and lots of words. And how do you deal with a large vocabulary where words are related, they're interrelated? So that's the topic. I'll now let Chanda continue.
Yeah, you're able to hear me, right?
Yes.
Thanks a lot, Asif, for the introduction, and thanks to all of you. Good afternoon. What I will do today is I will try to keep it as interactive as possible. So feel free to stop me with questions as and when you have them. Of course, I mean, because it is a webinar, we don't want it to get too interrupted, as Asif said. So let me, so what I will do is, I'm right now going to use a whiteboard, which I will use to describe this word embeddings. You're able to see my screen. I have a whiteboard. Is it
Yes, it's visible.
Yes.
Yeah.
Visible
So,
and very plain.
okay, yes, of course. Yeah, so I'm going to use this whiteboard where I will actually start writing. So let me do this. So what are we going to do? Today we are going to cover word embeddings, and I will try to cover two specific approaches. So one of them is word to vec. So I will go through word to vec in quite some detail, and I hope time permits. I mean, depends on how many questions are there and how interactive the session is. But I will also try to cover the glove embedding. So I don't know in this audience whether how varied the understanding on word embeddings is. So maybe just to have an understanding, can I have a quick, like we have around 14 participants. So is it possible to let me know if you have come across these words so far, or is it completely new, so that I know how fast or how slow to pace the whole videos?
Guys, if you know
Maybe
what embeddings, raise your hand. In this webinar, you can raise your hands. I see 2 hands raised, and we'll count the hands raised. So quite a few, 5.
okay, nice.
So about 1/3 of the audience knows word embeddings.
Okay, so that's okay. I will anyway. I mean, if for you some of the things may be a repetition. So in case it is, and you have some additional questions, it's okay. But because I'm not going to, what I will try to do is I will try to cover from the ground up. If you have any questions, you can bring them up. But some of them may be repetitive for you. Is that okay? So let me start with word to vec, which is, yeah. So I'm going to start with the first topic, which is word to vec. So you're seeing my screen as of now. So first, let us understand what are words in any vocabulary. Let us, for specificity, let us say we have the English language. Usually in what we look at are around 100,000 words in the English vocabulary. I mean, there may be more, but as far as the commonly used words, surely it is less than 100,000. So let us assume that we have around 100,000 words in English. Now, why do we want to convert them to vectors? The reason why we want to convert them to vectors is ultimately any kind of machine learning, any natural language processing we want to do, we need to convert words to vectors which are can be input into one of the ML algorithms. So whether it is, I mean, we can have a classification problem, like let us say given a text, we want to understand the sentiment, whether it is positive or negative. So that is a classification algorithm, or it could be some kind of where we are trying to do a translation, where translation is really trying to convert from say English to French. So any one of these, there are several algorithms, but ultimately all these algorithms need vectors to be the input. So given that that is the case, now the first problem, the 101 problem with words is to first convert them into vectors. So what is the most naive way of doing? So let us say we have 100,000 words that I mentioned. So these are W1, W2, W3, dot, 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 up to W 100,000. So we want to convert each one of them into a vector. Usually the most naive way one uses is called the one-hot encoding. And this is typically used not just for words. It is also used for any what are called as categorical variables. So categorical variables are basically variables which are one out of several. Like let us say the days of the week. You have Sunday to Saturday, Sunday, Monday, Tuesday. So you have 7 such possibilities. So whenever you have these categorical variables which are 1 of 7, here it is. It so happens that it is 1 of 100,000. So the typical naive way one does it is what is known as the one-hot encoding. So what you mean by that is you say W1 is the vector which is 1 only at the first position. So you treat it as a 100-dimensional vector, and you say that W1 is this, and what is W2? Obviously, it is going to be 1 at the second position and zeros everywhere else. So again, it's a 100-dimensional vector. So this is the way it is done, the most naive way. And of course, W 100,000, which is the last of these words, would have been one which is 0 everywhere and 1 only at the last position. So this is the one-hot encoding approach that is done in as the most naive approach to convert words to vectors. Now, the thing is, first of all, there are many problems with this. Okay. What are the problems? Can somebody try to list out these problems, or should I go ahead? I mean, I don't know if it can be interactive. Asif, how do you suggest? Should I wait for?
Yes, this would be a good question for people for us to wait, and I have given everyone permission to speak, so people can chime in. Let's wait a minute. Anyone would like to chime in? And
memory alone, and then the processing time.
Yes. So this is, I guess, Kate.
Yes.
Yeah, memory problem because we are using huge vectors.
It's sparse, right?
Sorry?
Yeah.
It is a sparse vector, like the matrix.
Yes, it is a very sparse vector, and which means that we are not really using, even though we are having 100,000 dimensions, not all of them are getting used. Correct? Sparse vectors. So it is basically, we are saying we are having a lot of unutilized. That is what you want to say, right? Unutilized space in some sense.
Yes.
And the network issue, like passing data across the chip, the bandwidth that would be needed for
that is in some sense related to this. I think
memory.
Whatever you're bringing is related to this, but there is a more fundamental problem which I think is very important to identify. I mean, yes, these two are very valid problems. I'm looking for one more, probably a very obvious problem with this.
There's no relation between the words.
Of course,
Machine
yes,
learning.
that is, yes.
The context
no
is
relation.
not lost. Context is lost, right? Yeah, relationship.
Yes. So what it means, just for the sake of everyone else, is let us say we have very closely related words. Like for example, I would think of pros and cons. Now, pros and cons are two words which are they come always together. You very rarely say a pro without a con. So these two words, now in this approach of using each word represented by a vector, there is really no difference. I mean, you could have had something else like camel and pros and cons. All of them, they are as different from each other or as similar to each other. Whereas we don't want that. We want a representation where it is. So I will mention it as we want a vector representation where relation between words is maintained. So we want, in some sense, the pros and cons. So if we are thinking of some kind of a vector space, I mean, this is of course only 3-dimensional I have drawn here, X, but let us say we have a much bigger dimensional vector space, though not as big as this 100-dimensional. Now in this vector space, we would like, I don't know, the pro vector to be here, the con vector to be somewhere here. So it's not very far away. Whereas the camel, something which corresponds to the camel, is quite far. So this is what we want. This is the ideal situation, right? So to do this, to do this is what is our first goal. So we need to go from the one hot encoding, which was the naive approach, to a better representation, where we just saw, where a better representation, so which will address all these drawbacks. It will address not only the drawback that related words are nearby, but it also address in the process, it will address these two issues. The fact that we are no longer having to deal with 100,000 dimensional vectors, or the fact that most of the data is 0 and just one of them is 1. So all of them will get addressed. So this is one of the ways of doing it. I mean, we are going to start with word2vec today. So I will first go with word2vec, where how it is this whole process of going from one hot encoded vector to this representation where words have relation is achieved. And subsequently, I will go through another approach, which is the glove embedding approach. So these are the two approaches I will cover today. So let us go through the word2vec first. So word2vec, what actually happens is, Asif, in case there is anything where I have glossed over and you think there is something I need to emphasize, please suggest. Okay. So the way it is done in word2vec is, ultimately it is done with a neural network architecture. So let me just show the neural network architecture that is done. It is a neural network architecture where there is an input layer, which is basically having 100,000, which is essentially one-to-one with the number of words in the vocabulary. So there is an input layer which consists of that many nodes, and there is a hidden layer which is much smaller in dimension. Typically, for the purposes of in word2vec, quite often the 500 dimension is used. So this 500 is the number of dimensions in which we are representing these words. And once we represent in these 500 dimensional words, it is not one hot encoded any longer. It is they are more dense representations where we have continuous values. Unlike the case where only one of the values had a 1 and rest had 0, it is no longer the case in this reduced dimensional representation. And in this reduced dimensional representation, words also will have this relation. So for example, the vector representation for, like I said, an example of pro and con would be quite close compared to a third word, which is like camel. So the way it is achieved is we have this neural network, which is a fully connected layer. So I'll explain how it happens. So you have a fully connected hidden layer, and then you go again to the another 100-dimensional output layer. Now, 100,000, sorry, 100,000 dimensional output layer. Again, it is fully connected everywhere. And what is the interpretation here? So I'm just stating that this is the neural network used, but I have not explained how exactly the input is fed, what is the output, and what is the minimization done. So I have not yet explained all that. So I'm going to tell that right now. So let us think of some random sentence. Like, I had bread and butter for breakfast. I'm just giving a random sentence. Now, think of this is just one sentence. Now let us think of the whole corpus of literature. Whole corpus of literature that is available in English, right? So whole corpus of literature available in English, which means it could include all of Shakespeare's works. I don't know, all of Leo Tolstoy translated to English. And I mean, and it could have the encyclopedia, whatever. So let us say we are having all this corpus of information, and each one of these corpus ultimately is consisting of several sentences. I mean, I have just given one simple sentence here, but imagine that there are each novel or each story is going to have millions of sentences. Each sentence will have several words. Ultimately, it is going to be a corpus of literature which is covering all these 100,000 words with different ways in which the sentences are structured. Now, I'm just giving one example here. This is one example of a sentence. So the way this word2vec is done is it is converted into what are called bigrams. In fact, it could be engrams, but I will start with bigrams, and then the generalization to engrams becomes kind of straightforward. So let us say we, out of this sentence, we are considering all possible bigrams. So that means I and had, because they are the first two words. And then you have had and bread. This is the second bigram. So bigrams are basically all these groups of two words which are occurring one after the other. Now, in a straightforward fashion, we can also consider trigrams and then 4grams and engrams in general. So I'm just starting with the example of bigrams. So let us say we had this I had bread, and so you can construct all these bigrams for this one sentence. Now imagine instead of just this one sentence, we had all these sentences coming from the entire literature. You'd have had tons of these bigrams. Now, what are we going to do with these bigrams? So if you go back here, if you see, there was this neural network where I said there is an input layer which consists of 100,000. So what is done during the training phase here is the input is the first part of the bigram. So for example, in this case, I and had. So the input vector corresponds to really the, let us say the word I in this lexicon, in this whole vocabulary, it was probably the fifth word, for example. So let us say it was the fifth word, which means we are having an input which is 0, 0, 0, 0, 1, because that is how we have defined the one hot encoding. And then 0 everywhere else. So we are feeding in this vector, which is the first part of the bigram I, had. And the output is going to be the second word had. And let us say the had was actually the word number 2, right? So if it was the word number 2, it would have been 0, 1, and then everywhere else is 0. So this is the input and this is the output. And because this is a fully connected layer, let us say this is represented by a weight matrix W. So in any neural network, we have a matrix. So here the matrix would have been, let me say this was, the vocabulary size was V, which is 100,000 here. There would have been a matrix of dimension WVN, which is going to connect this vector to the vector in the hidden layer. And then likewise, because there is one more fully connected network here, it would have had a W dash, another matrix, which will connect from N to the same V. So what we have done in the process of looking at these bigrams and feeding into this network that I just drew. So let me redraw the network because I don't want to go back and forth again and again. So I have this, and then I have this, and then I have this. So this was size V, this was size N, this was size V. V is of course much bigger, around 100,000. And N is much smaller, around 500. So we have this whole lot of bigrams where the input is I and output is had, or it could have been had and the output is bread. So you'd have had, imagine that you're creating these bigrams from the entire corpus of literature. So you have a whole lot of training vectors. You have a training and the corresponding, the training input and the training output. So training input and output is available. And you have this fully connected W and W dash, which you do not know, right? So the what is done in the process of training the word-to-vec model is to arrive at the W and W dash, which ends up predicting the appropriate output for the given input. So the input being the first part of the bigram, and the output being the second part. So, so in some sense, let us say the input word was, let me call it, what shall I call it? I'll call it VI. Let us say VI was the input. And this is getting multiplied by the matrix W. And let us say the VI is I represent it as a row vector. Okay. And this row vector is multiplied by a matrix. So this row vector had dimension of V, right? It is basically it is a 1 cross V matrix. A 1 cross V multiplied by a V cross N matrix. You end up getting a 1 cross N matrix. 1 cross V into V cross N becomes 1 cross N. And then this is multiplied. So this was the W. So this was the VI. This is the W. And then you have one more matrix, which is N cross V, which is the W dash. So what do you end up getting? You have this VI multiplied by W multiplied by W dash. And this again becomes, because this was 1 cross V and this was V cross N and this was N cross V. So if you have a 1 cross V matrix multiplied with a V cross N matrix and multiplied with a N cross V matrix, you finally end up getting a 1 cross N matrix, 1 cross V matrix, right? 1 cross V into V cross N and N cross V becomes a 1 cross V. So this again becomes a vector of dimension V. Now the only catch is that here it was a one hot encoded vector. So only one of them was fired. Like if you see the 001 that was corresponding to the word I, and everywhere else was 0. Whereas what we finally have is going to be values in all these places, A1, A2, up to AV, right? Now we need to somehow convert this, which is occurring in all these, which is having values at all these places. We need to convert it into something which is uniquely determining the word had, because had is a only one of, for every input, we are only having one unique output in the bigram. So this is done using the approach called Softmax. So the way this is done is, whenever you have a, so what we finally had is a AN cross AV. Now from here, we need to go into something which is only having one at one of the places, right? Because only then we can really make the connection between the input and output. So the way this is done is through the Softmax function. So the Softmax is essentially the way it works is these are all values which could have been double values, which could have been positive or negative. So the way the Softmax function is defined is you convert these to probabilities. So you do, for each value, you do an e power a1, e power a2, dot, 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 up to e to the power of av. Now, when you do the exponentiation from here to here, you're guaranteed to have all positive numbers, but then they are still not probabilities because they could have been bigger than 1. So you actually go through a normalization step where you do e power a1 divided by summation of e to the power of ai, and so on up to e to the power of av by summation e to the power of ai, where this I index is over all these values. Now we are guaranteed that these are actually the having the same meaning as probability, because first of all, they are all positive, and if you add all of them, they become 1. So what is done is from here to going to this, we look at the one which is maximum. So let us say we have some vector which was 0.1, 0.1, and then there was a 0.8, and then there is a 0.1, and then zeros everywhere. So if this was what this was, from this, the maximum value is 0.8. Therefore, we conclude that the word which is predicted is 0, 0, 1, 0, 0, 0. And so this is how the Softmax, I mean, this is, I'm sure those of you who have already gone through Softmax in the past, I mean, you know about it. I'm just explaining so that we are...
Quick question.
Yes,
Quick,
please.
before you scroll that up, at the equal, the 1 times v, the v times n, the n times v, and then that's equal to, I cannot read that.
Sorry, I think I should have, I'll...
Just what are those letters?
Yes, yes, yes. Let me erase that and rewrite.
Okay, thank you.
How do I erase it? I'm trying to figure out. Or let me do one thing, since I'm not able to erase it.
Just right above it.
Yeah. So let me go back here. So what whenever we have matrix multiplication, the way it works is the 1 cross v into v cross n becomes a 1 cross n matrix, and 1 cross n matrix multiplied by n cross v becomes a 1 cross v. So this was a 1 cross v matrix, a row vector. 1 cross v is basically a row vector multiplied by a matrix which is v cross n. This is the matrix multiplication, 1 cross v into v cross n into n cross v. You again get a 1 cross v matrix. So okay, this was a one hot encoded vector. This is the weight matrix W. This is the weight matrix W dash. So these two are unknown. So as of now, when we are starting with this whole word-to-vec training, we only know that there are these bigrams. There is this, like for example, in the example I gave, there is a I for a word I, you had the output had. And then for the word had, you had the output bread. So all you knew was you have this input vector and you have a weight matrix which you do not know. And using this unknown weight matrices, it is going to create this 1 cross V. Now, what we have done is out of this 1 cross V, we are trying to predict the word which is most likely to occur using this concept of softmax. Because what you have in this 1 cross V is a vector which is having values in all these. I mean, unlike the one hot encoded vector, which was having only a value of 1 in one of the dimensions and zeros everywhere, we have something which has values everywhere. But if you look at what we had as our output, we had only one of the words being fired. So to get that, we go through this approach of softmax and predicting the output to be the one which has maximum value for the softmax. So now this is a standard neural network which can be trained. So the training uses what is known as cross entropy, because whenever we have, so we have this, like I said, we have this pair of I, and there was a had. We had a had, and there was a bread. And so each one of them is a vector, and there is a corresponding vector here, and we train this. So our job is to identify the values of w and w dot dash, which end up achieving this training. So there are standard ways to do it. I mean, we can use keras or any other approach, but essentially it is a training of a neural network using the standard method of gradient descent, because we have an input and an output, and our goal is to figure out what the w and w dash are. Of course, it's not going to be straightforward, because it is the corpus is really huge. We have to train over all possible bigrams in the entire literature. And I'm starting with bigrams here, but in reality, we don't do with bigrams. We do with engrams, where typically we do n is equal to 5. I think, Asif, is that right? We use n equal to 5?
Yes.
So yeah, so normally we use n equal to 5. I mean, this is how the best word-to-vec models are built. And there are also, I mean, I have glossed over one part here. There are two approaches here that are taken in this whole word-to-vec approach. I have started with bigrams and said that we could go to n equal to 5, which is 5 grams. But there is also another, there is a bag of words approach, and there is a skip gram approach. There are these two approaches used typically in word2vec. So what do they mean? In bag of words.
I have one question.
Yes, please.
Sorry. So actually, how did you ensure that the, like in your previous example, that the third or the fifth one will have the highest probability, like you showed in that example 0.8, right? So
No, that was just an example. What I'm saying is, let us say I start with a 1 cross V matrix, and I start with some random weight matrices which are V cross N and N cross V. I don't know. I'm just starting. Usually the way the training works is we iteratively figure out what is the weight matrix which is going to achieve the output that we want, right?
Oh, okay.
In any neural network, we start with the way the neural network works is it uses this gradient descent to gradually reach the W and W dash, which is the ideal W and W dash.
Okay.
Right?
So
in neural networks,
know the answer, but then you try to design W and W dash so that you approach close to the answer, right?
Yes, exactly. So that is the gradient descent approach. And there is a whole technology for doing gradient descent. Whenever we have a softmax and we have the actual output, and that there is a loss function called as the cross entropy. In case there is something called cross entropy loss. So this loss function is what is minimized. So the whole neural network works on minimizing this cross entropy loss. And as we keep minimizing this loss, we keep getting to better and better W dash.
Okay. Thank you.
So you got it,
so,
right? So we have this training vector,
Chandra,
which is input and output. So we have an ideal input and ideal output. This is what we don't know. We start with some random matrices, and then we gradually, using gradient descent, reach the W and W dash, which comes up with the minimum value for this cross entropy loss.
Chandra, how many layers are needed typically for this?
In word2vec is just one layer. Word2vec is the approach is just using one single layer. That is the beauty of it. I mean, it will take a long time to train, but it is just one layer, one input, one hidden layer.
So here at least you are okay.
For more technical languages, let's say like in the scientific languages, does an engram with n equals 5 still apply, or do you prefer to a little bit?
Yeah, tell again. What is the question? With n equal to 5?
For more technical languages, let's say in the scientific community or in medicine, where
Yes.
not English, or if it's not spoken language, do you
Yes.
increase the n, or does n equals 5 still hold?
Normally n equal, I mean, it is a flexible parameter. I mean, you can try with different hyperparameters, but normally I think in Word2Vec, the standard, see whatever has been done and published, which we can end up, see, we don't do this training every time we come across a problem in natural language processing. So what we do is we borrow the embedding vectors that have already been created, and they are available publicly for download. So when we do that, normally the n is equal to 500. That is the dimensionality of the words, and n equal to 5 is what is typically used to. And also, I didn't yet explain what bag of words and skipgram is, but the skipgram is what is typically considered as the better approach. I mean, it gives more accurate values for the word vectors. Did I answer your question?
Yes, thank you.
Okay. Okay. And yeah, so this was a point which I have not explained yet. So I said there was, let us go back to the same sentence I had. I had bread and butter for breakfast. And let us say I'm looking at 5 grams. So if I look at 5 grams, 1, 2, 3, 4, 5 is a 5 gram. Then had bread and butter for is the next 5 gram. And then bread and butter for breakfast is the third 5 gram. I mean, here we don't have really any more 5 grams, but of course, when you are having a much bigger corpus, you are going to have many more 5 grams. Now in this 5 gram, there are two ways in which you can look at the input and output. So let us say you looked at the input as bread. You could have used the output to be I, or it could have been had, or it could have been and, or it could have been butter. Basically, it is all the surrounding words of bread. I, had, and butter, right? So this is called the skipgram approach. Skipgram, where you are using one word to predict multiple. But then there is another approach, which is the bag of words approach, which means you start with I, had, and butter as the input. And so this was the input, and this is the output. Okay. Now there is another approach where you choose this as the input, and the output would be the word in context. So here the word in context is predicting the other words which are surrounding it, whereas here the bag of words is predicting the output. So this is called the bag of words approach. So, I mean, I'm just mentioning this because there are these two approaches to doing Word2Vec. Whatever architecture I showed, practically with slight differences, you can use it to do either this or this. And experimentally, this is what people prefer rather than this. I think it takes slightly more time to train, but this is what is giving more accurate results. So this is the skipgram approach. Yeah.
Just a quick question. So the W and W1, would it have a reversed values in the bag of words?
No, actually they are called the dual. I mean, one is not the inverse of the other. So it's like this. So your V input times W times W dash is equal to your V output, right? This is, and you're asking whether W dash and W are in some sense transpose of each other. They are not.
No. So no, I was asking for the skipgram and the bag of words. So the W and W dash, become vice versa. Like W dash will become W.
No, I don't think so. No.
Oh, okay.
No.
Okay. Because I thought I had
two different approaches. Yes.
I see. So how do you give I, had, and butter as input? Because there is one hot encoding. I will have one hot encoding. I had will have one hot encoding. So you
So
combine
the
all.
way it is done is then there are multiple neural networks considered. So you have this. So you consider not just one, but you consider like, you got it? I mean, you consider if you had I had and butter, one of them would be the I, another would be the had, and then and. So you have basically you have four of these. And I mean, four layers which all get connected to this hidden layer.
It's like a summation.
Yes, so basically it is the same weight matrices get. So if you had a weight matrix W here, the same weight matrix will apply in all of them, but it is just that the inputs are different.
So so the first multiplication, which is Vi into W, will get summed up for 4 words, like I
Correct.
had and butter. Okay.
Correct.
Oh, okay.
Correct.
Okay.
And then the output is only to one here. Whereas in the bag of words, so this was the bag of words approach. Whereas in the skipgram approach, what would have happened is the converse. You would have had one input and then the hidden layer, and then it will end up predicting four different words. So you would have.
Oh, there'll be 4 spikes in the Softmax, right?
Yes.
You don't need 4 different output, but 100K output will be there, in which 4 of those outputs will have high value, high probability.
No. We actually consider 4 layers at the output, but with the same W dash for each one of them.
Oh, okay. Got it. I see. But it'll be the same value at the output. Like for all the W dashes, the output has to be the same because the N is same. W dash is same. So the output will be the same.
Okay. What you're saying is because it is the same vector. No, when you are doing the minimization, see, we are trying to ultimately minimize the cross entropy loss, right? Hello. Sorry.
145
I think there is some background.
Shankar, I'll mute Shankar.
Okay.
Yeah, he's on mute now. Go ahead.
The way it works. So the way it works is you're saying because it is the same W dash, you will end up having the same output vector everywhere. That point makes sense.
There'll be only one output vector.
There is, but we use all these to do the minimization. I mean, the fact is, if you had only one W dash, when you are trying to make the minimize the loss, you would have got only for predicting one output. Whereas you're trying to come up with a W dash, which is in some sense predicting not just one of these context words, but the others also.
Oh, I think you are subtracting.
So the training really depends on the fact that there are multiple layers.
Got it. I can imagine a little bit, but I will wait for your further lecture.
No. I mean, what you're saying is absolutely right. If you have a given W dash and if you have a given vector, the fact is that it is only going to have one output at a given point, and if you exponentiate it and give it, you're only going to have one value for the predicting the softmax. But the way it works is, as far as training is concerned, I mean, this is we are not ultimately going to use this to predict any skipgrams. We are going to use this whole network to there is a training data, and once the training data it determines the W and W dash, we are done. We are not going to use the W and W dash to later on do the actual prediction of context words.
Got it. So you take one of those matrices as the embedded embedding and then use it downstream.
Exactly. So for example, let us say you have found the W matrix, that actually becomes your embedding, because W matrix is, it's a, as I already told you, it is a V cross N matrix, which means every input word, which is a 1 cross V matrix, will get converted. Sorry, yeah, every input matrix will get converted by multiplication into a vector which is of n dimensions, because this was a 1 cross v matrix multiplied by a v cross n, it became a 1 cross n. So any word, like for example, I said I, which gets multiplied by w, which is a v cross n, I mean, this becomes a vector which is of n dimensions now. Is that clear? And this is no longer a one hot encoded representation, it is a dense representation. So this is how once we have w and w dash, we end up having vectors which are n dimensional for each one of these words.
So I have one more question. So now the W is of importance after you do all the training, because that is the transformation from one hot to the embedded vector.
Yes.
Do you throw away W dash, or will it be of any use?
No. I mean, we could have used W dash also as representation. It's not thrown away. I mean, I think in word2vec, both have been used. I think experimentally, either one of them works as good as the other. There is no reason to use one as compared to the other.
Got it.
So we could have used W to get vectors out of words. We could have also used W dash
to get the nearest words to the vector.
Yeah, see, so long as we use one of them consistently, we still end up having a conversion of whatever is the v-dimensional vectors to n-dimensional vectors. Either one of them can be used to get the vectors from words. I mean, they are called dual representations. You could have used either one of them, it doesn't matter.
Chandra, you have a question asked by one of the participants. Does bag of words pay respect to the order of the words?
No. Bag of words does not, it does not pay attention to the order. That's a good question, but it does not.
Thanks.
At least the way the word-to-vec neural network is defined, it does not pay, because it is a bag of words. That is why it's called bag of words. Neither does skipgram. It is just that when you are having a whole lot of these skipgrams, in some sense you end up having because more often you would end up having words which are only one word away coming more often than words which are coming 5 words away. So just by the fact that in the huge corpus, you end up having more cases where words which occur one after the other end up happening frequently. But as such, there is no, in this whole architecture, there is no order used to define the which is coming first and which is coming later and how much later and all. Okay. So there was one more thing which I wanted to cover before I wrap up on word2vec. So at the end of all this, okay, ultimately the proof will be in what are the nice properties that have come out of these word2vec vectors. So some of these nice properties which have been experimentally observed, like king minus queen. It turns out that this is equal to man minus woman. So what I mean by that is the king is a vector. It's a word which has a n-dimensional representation. After having converted the king into using the W into an n-dimensional, likewise, queen also has an n-dimensional representation. Man also has an n-dimensional representation, woman also. So it turns out that when you do this word2vec, originally it was all one hot encoded. So a difference between any two vectors, it would be equal to the difference between any two vectors. There is no connection you would have got, because the difference would have been only having ones and minus ones at two different locations. and those two would be different from for whatever the ones and minus ones for any other two words, right? Whereas in this n-dimensional representation, it turns out that when you convert king to an n-dimensional, queen to n-dimensional, and you do this minus this, you get something very close to this minus this, which means that Word2Vec has actually understood the English language. And this is not, I mean, this is just one example. There are more, I think, France minus Paris. I mean, this basically the country minus the capital, it turns out that it is equal to India minus Delhi. So this means if you convert these to vectors in this n-dimensional representation, there is a this basically tells that how much is a country different from the capital of the country. So again, it's a very nice relation. I mean, these are all close. It's not that it is exactly equal, but when you do this calculation, it turns out that you get some values which are very close. So it means it really has, it is behaving like proper vectors, where the relation between words is coming clearly, having done all the neural network training. Okay, so this is about Word2Vec. Any other questions? I will take it now. Otherwise, probably with a brief pause for 5 minutes, I will go on to glove. Asif, do you think we have time for covering glove, or is it?
Yes, we do have time.
Asif, you are not audible.
Oh, 1 second.
Asif, you are not audible. Am I audible?
Yes.
I hear Asif.
I can hear both of you.
There's time for glove.
All right. So, Chanda, there is a question. Can you guys hear the question? Chanda, for some reason, you're not able to hear me. All right. So, guys, there is an open question from Dave. Chanda can't hear it. Can one of you please repeat it for him? Look into the question and answer panel and read out the question for him.
That one he already answered, I think.
No, he has posted a new question.
Okay. I do not see the name.
Instead of doing a Softmax, why can't you pick the? That's the question you're talking about.
No, there is a question. All right, maybe that question is just meant for me, so we'll skip it.
Yeah, there is.
I have a question. Chandar, can you hear me? Chandar, can you hear me?
Chandar, can you hear us? Asif, can you hear us?
Yeah, I can hear all of you.
Okay,
For some reason.
Chandar has a problem.
Okay, let me give him a call. One second, guys.
Okay. Hello, Chandar.
Oh my gosh, it's my best friend calling me again. I wonder if something's wrong. This is only the 12th.
Asif. So you're able to, okay. But I am not able to hear anyone. Should I disconnect and reconnect?
No, we're able to hear you, Chandar.
Yeah, I hear you.
Okay.
But I think we can hear him. He cannot hear us on the.
Yes, there's some audio. So I've requested that he continue on with glove. Guys, I'll take the question at the end. Hopefully we'll have a resolution of his issue.
Hello?
Chanda, proceed.
Hello.
Yeah. So you are able to hear me, right? Let me then continue with glove. So let me probably move on.
Can you hear us?
So any questions anyway? I see one question here.
Listen, if you look at
I see a question here from Dave. Should I, probably I'll go through that first. Is there any way to make word embeddings that depend on the context because the same word can mean different things depending on the context. For example, so this is I think, Asif, this is something that you are going to cover in probably next week or the week after that.
That is right.
So,
Contextuality.
though I cannot hear you, Asif, I think you are acknowledging it. Yeah.
Yeah.
Okay. So yeah, I don't know why what happened to my audio. I don't know. Surprised. Let me try. Just quickly, let me try with my microphone.
Krishna.
Okay. It's okay. Let me continue because I'm not able to figure this out. Yeah. So yeah, Asif is going to cover this in a subsequent lecture. But yeah, in Word2Vec, what you are saying is spot on. There is going to be the same vector for the word, regardless of the context in which it occurs. So that is a drawback of Word2Vec. Yeah. So let me go on to glove embedding. Any other questions? There is no other question here. Does the conversion here have to be in the same set of dimensions? Does the conversion here have to be in the same set of dimensions? I'm not sure what the question means.
Let me take this. Yes. See, what happens is it's a bottleneck. A Word2Vec is a bottleneck. You go from
Anyway, I didn't understand the question, so let me move on to glove embedding.
Okay, I'll answer that later. Yeah, go ahead, Chip.
So I have covered the Word2Vec, and so before I go to glove, there is one small, probably I will addendum to Word2Vec, which is in Word2Vec. If you noticed, we used individual words, and from the individual words, we came on to the vectors, using starting with one hot encoding and then moving on to the vectors in the lower dimension. Now there is a slight improvement that one can do on Word2Vec using what is known as word piece, where you don't do one hot encoding on the words, but you do one hot encoding on word pieces. And why is that done? Because many times there are subwords which make, like for example, the very word subword. So in some sense, subword is the word sub is not a word by itself, but it occurs in sufficiently many words as a prefix that it actually makes sense to treat it as a word piece, and you do one hot encoding on this word piece rather than on the full word. And it turns out that doing this does an improvement on Word2Vec, and there is an algorithm called FastText, which goes through this approach, where instead of doing Word2Vec on the word as tokens, it does a similar architecture on word pieces. So I thought I should mention this for completeness. So let's go on to glove encoding. What is the meaning of glove? First of all, glove is an acronym for global vectors. So nothing fancy about it. They're just global vectors. And what is global about them? Why it is global compared to Word2Vec? I mean, the reason it is considered global is in Word2Vec, we look at either bigrams or trigrams or engrams, which means we are looking at like 5 words at a time, for example. So at a time, we are not looking at the entire global corpus of words. We are only looking at any given point. We are looking at 5 words at a time to come up with what is the input and what is the output. Now, global vectors is the approach is taken is slightly different. So what is done is, let us say we have the same 100,000 words. So you have W1 all the way up to W100,000. Now you write it along the column of a matrix, of a square matrix, and then you have the same W1 all the way up to W100,000. So you have a matrix which is basically having the rows as well as the columns as these words. And what do you have in the values? So the values, for example, the diagonal entries really don't matter. So let me leave out the diagonal entries. The off diagonal entries, the 1, 2, W1, W2, that's really, it is denoted as X12. It is the number of co-occurrences of W1 and W2. Similarly, W13 would be X13, which is the number of co-occurrences. That means the number of times the word 1 and word 3 co-occur in the entire corpus. So how is the corpus defined? Corpus ultimately is a collection of documents. So like I said earlier in my previous example, I said all of Shakespeare, all of Leo Tolstoy. So you have, let us say you have around 1,000 documents. I'm just, there may be more. Let us say you have 1,000 documents. And let us say each of the documents has around 1,000 words, which are basically sentences in the form of words. Let us, I mean, this is of course far from the truth. In general, there are many more documents and many more words per document, but just for specificity. So let us look at each one of these document, and in each one of these document, let us look at the co-occurrences of the different sets of words. So let us say there was a word 1, which was like, for example, I mentioned bread, butter. So let us say word 1 is bread and word 2 is butter. Now, how many times do they co-occur? And then not just bread and butter, but bread with each one of these 100,000 words. So you look at how many times they co-occur in each of these documents, and you sum up all the co-occurrences. So it's going to be a huge number, but then there are these co-occurrences for a word 1 with each one of these all the way up to X1 100,000. Okay, so likewise you have these words here, and it's a symmetric matrix because number of times word 1 and word 2 co-occur is same as number of times word 2 and word 1 co-occur. So you have an X21 which is actually equal to X12. So you have these co-occurrence matrix. So this is the co-occurrence matrix. So in Glove, what happens is you first start with this matrix as your starting point, and from here you try to derive the vectors. So how is that done? So the way it is done is, first of all, let me call this matrix, which was C, which is the co-occurrence matrix, which we just defined. From here we define matrix of probabilities. So, and how is that matrix of probabilities defined? It is done by doing a dividing by the normalization. So if you remember, I said X12, X13, all the way up to X1 100,000. And of course, the first element is something which doesn't matter because it is the number of times word 1 and word 1 co-occur, which is practically all the time. So what is actually done here is you convert this into a probability matrix, P12, P13, all the way up to P1 100,000. Similarly, you have P21. This diagonal element doesn't matter. And then you have P31 all the way up to P21, P23, P22 doesn't matter. And all the way up to P2 100,000. Now, what is the meaning of all this? So the way it is defined is, I'll just write it here. Pij is defined as Xij divided by summation over Xi. No, sorry, summation over Xij. Summation over J of Xij. So this is what I mean to say. So this means what we are saying is while the absolute counts may be X12, X13 and all the way up to X100, the probability that word J occurs in the context of word I is the number of times it occurs divided by the total number that any of the words occur, right? So this is Pij, and likewise, so the way it is from here to here, you are converting the actual co-occurrence count to the probability of co-occurrence. So once this is done, we still haven't figured out how to get the vectors out of it. So there is a little bit of trial and error that is done. So the Glove paper actually explains it very well, but I will explain it here, and you can further read the Glove paper again. So let us say we want to come up with glove vectors. So let me say, let us say we come up with those glove vectors which have the same nice property. You remember in word to vec we had these nice properties: v king minus v queen is me, v man minus v woman. This was in word to vec. Now we know that this is our we want to achieve, because we have noticed that this kind of understanding that word to vec brought in was really powerful. So we want to arrive at this kind of a relation even for glove. Even for glove, we would like to get a embedding which kind of replicates this behavior. Okay, so the motivation is, but what we have is the PIJs. From here, how do we get this? So there is a nice argument in the glove paper. So I will probably what I will do is, the way to explain it, let me think of a third word, which is clothes. Okay, so corresponding to clothes, let me say I have a glove embedding. I don't know yet. I don't know what the glove embedding is. I'm going to argue for how that glove embedding can be derived from this PIJs. So let us say for clothes, there is a corresponding glove embedding called V clothes. Okay, it all sounds a little abstract right now, but very soon it will become obvious. So once you have vectors, you can actually do what is known as an inner product. So V king minus V queen. Let us say I do a dot product with V clothes on both sides. So because of the fact that V king minus V queen is supposedly equal to V man minus V woman, which I don't know yet, but I want it to happen. So which means I can take the dot product, which is the inner product of these vectors with this V clothes. And what do I end up getting? I end up getting V king dot with V clothes minus V queen dot with V clothes is equal to V man dot with V clothes minus V woman dot with V clothes. Okay, so this is what I have ended up getting if I assume that this relation is true, and I'm just doing some random third word. Now, how do I now connect this with my PIJs? Now, there is something interesting that one can see from, let us now, sorry. Okay. Let us now think of what can happen. P king clothes. So I'm not doing anything here. I'm just writing these different possibilities and somehow trying to connect these with these vectors. So I have, so what is the meaning of P king comma clothes? It means the number of times the probability that clothes will occur whenever the word king occurs. So that is the probability of P king comma clothes. So let me write P of queen comma clothes. This means what? This means the probability that clothes will occur whenever queen occurs. Man, clothes. I'm writing these four P, woman, comma, clothes. Okay, so what do we expect as far as probabilities to be concerned? We know something like this has to be true. King is to queen. I'm just writing some very heuristic here. Okay, this is not very precise, but we know that we want something like this to be true. King is to queen as man is to woman. This we know has to be true if our words are in any if we have understood the language well. We know that king is to queen as man is to woman. Now, what does it say about probabilities? So whenever we have king is to queen as man is to woman, we expect P king clothes divided by P queen clothes to be equal to P man clothes by P woman clothes. See, unfortunately, I can't hear any of you. If any of you is asking question, maybe I should look at the. Okay, so far no questions. I'm assuming you are with me because I'm just trying to argue how we can get a glove embedding from these probabilities. So far I would like to get something like this. So this is what I would like to get. But what I have is this. What I have is this because of the fact that king is to queen as man is to woman. Therefore, it means that the ratios of the probabilities of clothes occurring in the context of king to clothes occurring in the context of queen is equal to this. So this is what we expect whenever we say that there is a similarity in this fashion. But from here, if we need to get these this kind of an equation, here we have a ratio, but here we have a difference. So this is the insight that came in the glove paper. It's a very nice insight. I think the way they have argued is this can work only if, which means v king comma clothes should be related to logarithm of p king comma clothes. Because if this were true, p king, this ratio gets converted to a difference. How does that happen? Because if you take logarithm of both sides, you end up getting log of p king comma clothes, because log of a by b is log a minus log b. Log of p queen comma clothes is equal to log of p man comma clothes minus log of p woman comma clothes. So this, we see that this ends up becoming whatever we wanted it to be. This is what we wanted. We wanted v king dot v clothes minus v queen dot v clothes to be v man dot v clothes minus v woman dot v clothes, because this is a relation which we like, which we want. We have seen in Word2Vec that it is a very nice relation to have. Therefore, what I have argued is using the co-occurrence matrix, and from the co-occurrence matrix coming to the probability, we see that we can get a similar kind of a vector which is called the glove vector. So now the glove vector is defined as logarithm of p, I shouldn't call it king any longer. Maybe I shouldn't even call it like that. So what I want to say is,
Chandra, a time
v
start wrapping now
of a word 1 dotted with v of a word 2 is in some sense equal to logarithm of p word 1 word 2. So this is what, if this were true, then obviously everything else follows. So if we can come up with a vector which follows this, we end up having the glove embedding. Now from here, what do we do? I think, so the way the next step is done from here is, let me try to recollect. So there is a minimization of the.
Chandra, time check. Yeah.
Let me just quickly go through the glove embedding paper which I have. Just a second.
Oh my gosh, it's my best friend calling me again.
Hello? Yeah. Almost. I'm almost done. I'm just finishing the last part. Okay. Yeah.
Nice. linked.
Yeah. Okay. So I think, yeah, more or less this is what it was. So from here, what is actually this dot product? We call it a dual vector. So let me mention this. The way it is done is you have W1 dot VW2 minus logarithm of W1 W2. Okay, and this is the error. So here, what we do not know is the vectors. We do not know these, but we do know these, right? So, and this is the error function is defined as this minus this whole squared. Yeah, this is the part I just referred to. So the way the error function is defined, you are summing over all combinations of Wi, Wj. So I should no longer call it Wi, Wj, Wi, Wj. So what we have here is we have a whole lot of probabilities which are actually coming from the co-occurrences. So this is something we know. This is something we know. This is what we do not know. We do not know these vectors. And what we try to do is we try to minimize this is the error function, because we want the dot product of vectors to be same as the logarithm of the probability of co-occurrence. So we do this VWI dot VWJ minus log VWI we square it, and then we actually also add a weighting factor. That weighting factor I'll explain quickly. So this is the error function. So just like in word2vec, we were trying to minimize the cross entropy loss, right? In word2vec, if you remember, we had all these engrams. I showed the bigram case where we were trying to minimize the cross entropy error. Here, what we are trying to minimize is this error, which this error is the dot product of vectors, and we do not know what these vectors are. So we will start with some random values. So let us say we go to some n-dimensional. So ultimately, it becomes a similar problem. So if you have n-dimensional representations, let us say again we are doing 500-dimensional representation for these vectors, you end up having a weight. This is a 500 and this is also a 500. So you actually have a matrix of 500 into 500, which is similar to the weight matrix which we are minimizing. So you have a weight matrix which have all these weights, which is that weight matrix is being, so let me call that as some Wij. This is a weight matrix because it's a Vwi dot Vwj. In general, it is indexed by ij. And then you have log of Pij, which is something you know. So this is something you know, and you have a whole square, and then you are summing over all possible ij's, and you have a f, a weighting factor, which is made to depend on these Pij's. Okay. So why is this done? This weighting factor is made to depend because you want it to have a high value only if Pij is high. So that is why you have this weight matrix, and this error is minimized. And when this error is minimized, you end up arriving at, just like in word2vec, you arrived at the matrix. Here also you arrive at the ideal matrix, which ends up minimizing this error. And once you have the minimum value, you can use it to define your glove vectors, just like you did in the word2vec. So it's quite parallel. The fact is we are using instead of using Engrams, we are using the probabilities of co-occurrence, and then we are doing a minimization of this error. So more or less, I think I have covered glove. So any questions on this? I can take it now. Maybe I should look at the Q&A to.
Can you hear me? Can you hear any of us? Probably still not there.
Okay.
I hear you.
Is there a question on glove? what is an advantage of glove vector on top of the ordered?
Hello?
It is just a different approach. I think the people who the glove, when they wrote glove, it came after word to vec. I think the authors said that it is better, but as on date, there is the, I think both, there are different contexts in which each one of them works well. I don't think there is a clear which one is better. Asif, you have any comments on this?
Yeah. So the word to vec looks at local relationships. You looked at the skip grams and so forth. Now, the glove, because it's based on the co-occurrence matrix, it looks at more global relationships.
Unfortunately, I can't hear Asif, but.
Any questions, guys? I hope you got that.
Any other questions?
So
I
Asif,
posted in chat the glove paper.
Yes.
Asif, when Chandra was saying the goal is to minimize this error to get that V, WIWJ, minimize to what?
Yeah, see the error. See, in machine learning, the way.
Sorry, I'm not able to hear anyone. I don't know what happened to my audio. I have to get this fixed.
Let me include Chandra through the cell phone in this, so he can hear this. 1 second, Amridul, and then I'll answer you.
Sure. No rush.
Chandra, can you hear me? No, not yet. His cell phone is also not ringing. All right, so let me answer this. See, what happens is you need a loss function to train the weights. Ultimately, the point is the same. You need a lower dimensional embedding space, and you need the lower dimensional embedding vectors, right? So the question is, how do you find those vectors? They are weights, again, taking you from higher dimension to lower dimension, right? The hidden space. So now the question is, you know that you need weights. You can initialize it with some random values, but how do you train it? You need to create a notion of a loss function. So this loss function that Chandra is showing you, it's a very natural thing. It is saying that the dot product of two vectors in the embedding space.
The person you have called is speaking to someone else.
So it should be very close to the log of the log of the probability weights, right? So that is just that, because that makes logical sense. He explained king minus queen or something. So with that loss function written like that, you're basically saying that maintain that relationship, king minus,
I see.
Yeah, yes. And so now that you have a loss function, what can you do? Your random weights can now get optimized to the best weights that will essentially give you those relationships. And that is enough, in a sense.
Yeah, I see. It's not okay. Yeah. Very good. Can we scroll over that one just?
Yeah, I wish I could get you in the 1 second. I'll try him again.
Sure.
This has been a bit of audio issues. His phone is coming out busy for some reason.
Okay, there is a question. Yeah, I see a question for glove.
Oh my gosh, it's my best friend calling me again.
Hello.
Hey, Chanda, I'm going to pointed you at the speaker, my speaker, so that you can hear other people when people ask questions. Right. So
Tell again.
I have put this cell phone next to the speaker, my speaker for the web conference, so you can hear people's questions. Now, right, just to let you know. So go ahead and answer Dave's glove vector question, and the other questions that Mridul asked, I already answered.
Yes.
Okay.
Yeah, for glove vectors are the probabilities of, just a minute, let me mute here. Yeah, are the probabilities of co-occurrences the co-occurrences in the document or co-occurrences in an engram, or these are the global co-occurrences. That is why it is called global. These are the global co-occurrences across all the documents. Did I answer?
Yes, you answered that. To be more precise,
Okay.
what you do is you take a window of 5 words, a word and its neighbors on the left and neighbors on the right. So anywhere in any of the documents, if a word co-occurs with some other word in that window, you say that it has co-occurred. Dave, I hope that answers your question.
Can you please scroll up where you wrote that probability equation? Pij is equal to.
Okay, so Chanda, can you scroll up a little bit? Mridal is asking for something.
Okay.
Yeah.
Yeah. What are the?
Scroll up a little bit.
And is there a way to move this screen? Yeah. No. Oh, more. I think.
Should I go further up?
Yes, please.
Mridal, now ask your question.
No, I think the one you are right, Pij, where you define the probability, right? Pij is equal to when you're defining the matrix here.
Right.
No, further up here.
Yeah,
this one, yeah. PID Xij, okay. For every J in the bottom, okay.
Is it clear?
Yes. It's better.
Okay, maybe you are referring to this. This should have been K.
Yes. Some arbitrary word K, yes.
Yes.
Yeah.
Some arbitrary word K here, and not that J. Okay. Thank you.
Yes.
I have a question. So I'm just trying to put it in perspective, like the whole thing, why we are doing this, the Engram and like 2 gram, 3 grams, Engram basically. So we are trying to predict the next word, right? Is that the goal?
No, we are not predicting. I'll let Chanda answer it, but the bottom line is the original one-hot encoded space is useless because all the words are orthogonal to every other word. The dot product between 2 words is 0, means none of the words are related. We are trying to come up with another hidden space, a latent space or embedding space in which the words mean something. They're near other words that have similar or related meaning, semantic.
So we are just addressing the embedding part.
Embedding part, yes.
Okay,
so word embeddings are all about embeddings. And now Chanda will say more. Chanda, would you like to add more?
I think Asif, you covered it. So there is nothing more. With one-hot encodings, 2 words have no relation. So we do not want that. We would rather go with words where the context and the relation becomes apparent. See, also the fact is, once we train this on vocabulary, we do not want each and every time to relearn the vocabulary because the same vectors can be reused in multiple contexts.
Makes sense. Yeah. So once it created word embedding, like it could be in any dimension, and then it can be reused wherever needed. Is that correct, sir? Correct understand?
Yes.
Correct.
What people do is train the word embeddings on huge corpus of documents. And once they have been trained, people use those embeddings in their work.
Yeah. See, many times in our real world problems, we let us say we want to do a sentiment analysis, or let us say we want to do some classification of a set of documents into different kinds of topics. For example, our training will consist of very less data in a normal, let us say we have the set of documents and we have the set of subjects that need to be assigned. We may have a training data of just some 1,000 data points. With that, we cannot really hope to interpret the entire language. Whereas we know that this language is English, which is already coming from the corpus of literature we are aware of. So we train it beforehand on this corpus. And then we are left with a much simpler training to do with, we should be able to achieve it even with the 1,000 data points.
I see. So do we have any libraries where which can be directly used with problems like this. If somebody wants to solve the NLP problems, I guess these algorithms are already implemented and can be directly used as libraries.
Chandra, you got the question? Chandra, you got
Sorry?
Did you get Pradeep's question?
No, I didn't get it. Tell again.
So the question that he asked is that, so he assumes that there are libraries that can help us do word-to-vec and glove so that we can just use it. These embeddings are available, we can directly import and use it.
Correct. Yes.
Yes. So Pradeep, these are all there, both in Keras, PyTorch, everywhere. These embeddings are well available now. And these algorithms are fully implemented. So using it is just one line of code, but the important thing is to know and use it.
Right, correct. Thank you very much, sir. Thank you very much, Chandra.
Any other questions, guys? All right, guys. And then
No, thank you.
I'll close this session. Thank you very much. Those of you who are waiting for the next session, which is on Python, please, I'm deferring it by 1 hour. Let's regroup in 1 hour and then we'll do it. Right? I need to grab lunch. So I'll post it on Slack. You're welcome. It's again an open session. Everybody is welcome.
3 o'clock, Asif.
And thanks a lot to everyone for participating. I'm sorry about the technical issue on my end.
No problem. And thank you, Chandra, for the great talk. This was fun for all of us to learn about word2vec. And announcement, guys, next week, we have yet another very illustrious speaker. He's Dilip Krishnaswamy. In India, some of you may have heard of the Reliance Industries. They are heavy, and now they are creating their own currency, blockchain and so forth, digital currencies and so forth. So Dilip Krishnaswamy is the Vice President of Research and Innovation. He's leading the blockchain initiative, and he'll be giving us a talk on 2 things. First, this coming week, he'll give us a talk on quantum computing. Quantum computing is a very hot topic, and it is going to change everything, including the way we do AI and so forth. So it's a sort of, I thought it would be a good thing to do. He has published papers in quantum computing. And in a couple of months, he'll also talk about blockchain and its relationships to all the computing and AI and stuff that we do. And he'll speak from the perspective of the implementations that he's doing. Those implementations have already won awards. They're considered tied in as the best in the world. So it would be good to hear from the horse's mouth. With those words, guys, I'll end today's session. Thank you for participating in this. I look forward to seeing you all again next week. Thank you.
Thanks, Asif.
Thank
Chandra,
you,
thanks
Asif.
a lot.
Chandra.
Thank you.
Thank you.